there, and welcome to the Sleepy Space Channel. Tonight, a quiet contradiction about the one star most of us think we already understand. Ask almost anyone to name a star, and the answer will often be Polaris, the North Star, the steady point that has guided travelers for thousands of years, simply by staying still while everything else in the sky turns slowly around it. It feels like the most reliable, most thoroughly understood star there is. And yet, when astronomers look closely, instrument by instrument, year after year, Polaris turns out to be one of the most quietly puzzling stars we know. Its brightness changes in ways that should not happen. Its distance from us is still not fully agreed upon. And its closest companion appears, by some measurements, to be far older than physics says it ought to be. Tonight, we will walk through what Polaris actually is, why something so visible to the naked eye has proven so resistant to precise measurement, and what its strangeness might be quietly telling us about the limits of what we think we know. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to hold. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Begin with the simple picture, the one most people carry without ever questioning it. Polaris sits almost exactly above Earth's rotational axis, which means that as the planet spins, every other star appears to wheel slowly around it through the night, while Polaris itself barely seems to move at all. From the North Pole, it would sit nearly straight overhead. Moving south, it sinks lower and lower in the sky, until somewhere south of the equator, it disappears below the horizon entirely. This single geometric fact, a star that happens to sit nearly in line with the planet's spin axis, is the entire reason Polaris became useful to navigators for thousands of years. Find Polaris, and you have found north reliably, without any other instrument, on any clear night, anywhere in the northern hemisphere. This usefulness has given Polaris a kind of reputation it has not entirely earned. Because it has been so dependable as a fixed point, the mind quietly assumes it must also be a simple, well-understood object, a single steady star doing one steady job. The truth, once examined closely, is almost the opposite. Polaris is not a single star at all. It is not simple. And the closer instruments have looked at it over the past 2 centuries, the more its behavior has refused to settle into anything resembling a tidy explanation. Worth a few unhurried sentences here is what a telescope reveals that the naked eye cannot. To unaided human vision, Polaris is a single, solitary point of light, slightly brighter than its neighbors, sitting quietly at the end of the Little Dipper's handle. This was the entire understanding of Polaris for the vast majority of human history. A point of light, useful, fixed, alone. In the late 18th century, careful telescopic observation revealed that Polaris was not alone after all. A second, much fainter point of light sat nearby, gravitationally bound to it, orbiting it in a wide, slow path. This second star, far too faint to be seen without magnification, had been hiding in plain sight for as long as anyone had been looking up. More than a century later, additional careful observation of Polaris's motion revealed something stranger still, a subtle wobble in its position that could only be explained by the gravitational tug of yet another companion, one too close and too faint to be resolved visually with the telescopes of that era. It would take many more decades, and eventually a space telescope capable of extraordinary resolution, before this third companion was finally captured directly in an image, confirming what indirect measurement had suggested for a very long time. So the steady, solitary point of light that has guided travelers for millennia turns out, on closer inspection, to be a small family of 3 stars, bound together by gravity, orbiting a shared center of mass, 2 of them invisible to anyone without a telescope, all 3 of them blurring together into what the naked eye perceives as a single, dependable point. The star we have trusted as our fixed reference was never alone. It only appeared that way because of distance. The same kind of distance that compresses complexity into simplicity. The same principle explored in earlier nights when considering how far away things appear smaller and stiller than they truly are. The brightest of these 3 stars, the one that does the actual work of marking north, is an evolved giant star, many times the size of the Sun, swollen well past the modest dimensions of an ordinary main sequence star like our own. If this star were placed where the Sun currently sits, its outer surface would extend a significant fraction of the way toward Mercury's orbit, a single star occupying a meaningful fraction of the inner solar system. Its 2 companions, smaller and fainter, orbit at very different distances. One relatively close, completing its circuit in a few decades. The other much farther out, taking tens of thousands of years to complete a single orbit around the central pair. A slow gravitational dance unfolding across a timescale that dwarfs the entire span of human civilization. But the structure of this triple system, while interesting in its own right, is not the part of Polaris that has truly unsettled astronomers. The deeper mystery lies in the brightest star itself, and in a particular category of star it belongs to, a category that happens to be one of the most quietly important tools in all of astronomy. In the early years of the 20th century, a researcher working through an enormous catalogue of stellar photographs noticed something remarkable about a particular class of star, one that brightens and dims in a slow, steady, repeating rhythm. These pulsating stars, swelling and shrinking, growing brighter and fainter on cycles lasting days or weeks, turned out to follow a precise mathematical relationship. The longer a star's pulsation cycle, the brighter that star actually is, intrinsically, regardless of how bright or faint it might appear from Earth due to distance. This relationship transformed these particular pulsating stars into something astronomers call standard candles, objects whose true brightness can be calculated just by timing how long they take to brighten and dim. Once you know how bright something truly is, comparing that to how bright it appears tells you, through simple geometry, how far away it must be. This discovery became one of the most important rungs in what is sometimes called the cosmic distance ladder, the layered set of techniques astronomers use to measure distances at every scale, from nearby stars to galaxies millions of light years away. Nearby distances can be measured directly through the gentle geometric trick of watching how a star's apparent position shifts slightly as Earth orbits the Sun, a method that works well for distances up to a few hundred light years, but fails beyond that, as the shift becomes too small to detect. These nearby, directly measured stars are used to calibrate the brightness relationship for the pulsating stars described above. And once that relationship is calibrated, those same pulsating stars can be found in distant galaxies, far beyond where direct geometric measurement is possible, allowing their distances to be calculated from nothing more than the rhythm of their pulsing light. Polaris. And because it is by far the closest example of this category to Earth, it should, in principle, be one of the most useful and most thoroughly calibrated objects in the entire field. A close, bright, easily observed example of the very tool astronomers use to measure the scale of the universe itself. This is where the story should become simple. It does not. The first sign that something is unusual about Polaris's pulsation came from tracking the size of its brightness swings over time. For most of the 20th century, the difference between Polaris at its brightest and Polaris at its dimmest slowly shrank, year after year, decade after decade. A gradual fading of the pulsation's intensity that continued for decades without any sign of stopping. Then, sometime around the turn of this century, the trend reversed. The pulsation amplitude began growing again, slowly climbing back upward, with no clear explanation for why it had declined in the first place, or why it chose that particular moment to begin recovering. No other pulsating star of this type has ever shown this particular pattern. A long, slow fade, followed by an unexplained recovery, observed over more than a century of careful tracking. Stranger still is what has happened to the timing of the pulsation itself. For the better part of 2 centuries that Polaris has been observed, its pulsation period, the time it takes to complete one full cycle of brightening and dimming, has been steadily lengthening, growing longer by a small but consistent amount each year. This kind of period change happens to pulsating stars as they evolve, as their internal structure shifts during the later stages of stellar life. But the rate at which Polaris's period has been lengthening is unusually fast enough to suggest the star is moving through some phase of its evolution more quickly than these kinds of stars typically do. Then, within the last couple of decades, this trend also reversed. The period that had been steadily lengthening for generations began instead to shorten year after year, with no settled explanation for why. One tentative idea is that the close companion star, swinging past during certain points in its orbit, might be gravitationally disturbing the pulsation in some subtle way, nudging the rhythm slightly off its expected course. But this remains speculation rather than confirmed explanation. The honest state of current understanding is that Polaris's pulsation has changed direction twice, in 2 different ways, across the span of recorded observation, and nobody currently has a complete account of why either reversal happened. This raises a question worth sitting with for a moment, the same kind of question that animated an earlier evening's exploration of the dark night sky. When a single, nearby, thoroughly observed object refuses to behave the way theory predicts, there are really only 2 broad possibilities. Either something genuinely unusual is happening to this particular object, some quirk of its individual history, its companions, its internal structure, or the theory itself, the general model used to predict how this entire category of star should behave, is missing something, some piece of physics not yet properly accounted for. Distinguishing between these 2 possibilities is exactly the kind of patient, careful work that astronomy excels at, or and exactly the kind of work that takes far longer than any single observation to resolve. If the pulsation behavior were the only puzzle, Polaris might simply be filed away as a single unusual case, an interesting but isolated curiosity. But there is a second, more fundamental problem, one that touches not just Polaris's behavior, but a piece of information that should, in principle, be one of the easiest things to pin down for any nearby star: its distance, the geometric method for measuring stellar distances. Watching the tiny apparent shift in a star's position as Earth moves from one side of its orbit to the other depends on measuring an angle so small that even slight imprecision in the measurement translates into significant uncertainty in the resulting distance. For Polaris, this angular shift has been measured by two different space-based missions, separated by roughly 2 decades, and a substantial improvement in instrument precision. The two missions do not agree. One places Polaris at a distance modestly different from the other, a discrepancy that might sound small in percentage terms, but translates into a meaningful disagreement about exactly how far away this particular star actually sits. Taken across the full range of distance estimates that have been proposed over the years, using various methods and various assumptions, the uncertainty in Polaris's distance spans a range wide enough that no single number commands universal agreement within the astronomical community. Several factors conspire to make this measurement unusually difficult for Polaris specifically, even though the underlying method works perfectly well for many other stars at similar distances. Polaris is bright enough that it can overwhelm the sensitive detectors used to make these precise measurements, introducing subtle errors into the data. It is also a pulsating star, meaning its brightness, and to a lesser degree, its other measurable properties are constantly shifting on their own rhythm, adding an additional layer of complexity to any measurement that assumes a star's properties are constant. And it has a close companion star, orbiting near enough that its gravitational influence and its own faint light can subtly contaminate measurements intended to capture Polaris alone. Each of these complications is individually manageable. Together, applied to the same target at the same time, they have made Polaris's distance an unexpectedly difficult number to settle. This distance uncertainty creates a kind of ripple effect through everything else astronomers might want to know about Polaris. Knowing a star's true distance is the foundation for calculating nearly every other physical property. How much mass it contains, how large its radius truly is, how much energy it actually produces. Without a settled distance, all of these downstream properties carry their own compounded uncertainty. The mass and radius figures used earlier in tonight's exploration, the comparison to Mercury's orbit, the description of its evolved giant status. All of these rest on a particular choice of distance, and a different choice would shift the picture meaningfully. And here the puzzle deepens further, because even using the most current and most carefully measured distance estimates, the properties that emerge for Polaris and its close companion do not comfortably fit together. The two stars, bound by gravity and presumably formed together from the same collapsing cloud of gas at the same point in time, should logically be the same age. Stars that form as gravitationally bound pairs are born from the same stellar nursery, in the same brief window of cosmic time. And there is no ordinary mechanism by which one half of such a pair would be dramatically older than the other. Yet the measured properties of Polaris's bright primary star suggest an age startlingly young by the standards of stellar evolution, a star that appears to have formed relatively recently in cosmic terms. Its close companion, by contrast, displays properties consistent with a star that has existed for a vastly longer span of time, old enough that the mismatch between the two ages, if both measurements are taken at face value, becomes difficult to explain through any conventional account of how binary star systems form and evolve together. A few possible explanations have been proposed for this age mismatch, none of them fully settled, each one illuminating something interesting about how astronomers think through this kind of puzzle. One possibility is the simplest, in a sense. though also the most unsatisfying. Perhaps the apparent companionship is some kind of coincidence or measurement artifact, and the two stars are not actually as gravitationally bound or as genuinely coeval as the evidence otherwise suggests. This explanation tends to be treated skeptically, since the gravitational binding between the stars has been measured carefully enough through multiple independent methods that dismissing the relationship entirely would require explaining away quite a lot of consistent evidence. A second, more intriguing possibility draws on a phenomenon first identified in the middle of the 20th century, when astronomers studying dense, ancient clusters of stars noticed something unexpected. Certain stars within these otherwise uniformly old clusters appeared distinctly younger than their neighbors, bluer and hotter than stellar evolution models said they should be, given that every star in the cluster supposedly formed at the same ancient time. These anomalously young-looking stars came to be understood as the likely products of stellar collisions or mergers. Two older stars in a binary system gradually spiraling together and combining into a single star that, through the violence and mixing of the merger, effectively resets its apparent age, behaving, for a time, like a much younger star than its true history would suggest. It is possible, though far from confirmed, that something similar happened in the distant history of the Polaris system, that its brightest member was once two separate stars, or absorbed material from a close companion in some earlier stage of the system's evolution, an event that left it appearing rejuvenated relative to its true age, while its remaining companion continued aging along its ordinary, undisturbed path. This remains a hypothesis rather than an established fact, but it illustrates how a single nearby anomaly can connect to a much broader category of stellar behavior observed elsewhere in the galaxy, in dense, ancient clusters, far from our own quiet stellar neighborhood. There is a third thread worth pulling on here, one that touches the broader models astronomers use to predict how stars like Polaris ought to evolve in the first place. These models, built from decades of careful physics, attempt to track how a star's brightness, temperature, size, and internal structure change over its lifetime, based primarily on its mass and its initial chemical composition. For the vast majority of stars, these models work remarkably well, matching observations closely enough that astronomers trust them as a reliable foundation for everything from age estimates to distance calibration. But these models, however sophisticated, still rely on simplifications, places where genuinely complex physics is approximated or set aside entirely, because including it fully would make the calculations intractable. Stellar rotation is one such simplification. Every star rotates, some quickly and some slowly, and this rotation can meaningfully affect how material mixes within a star's interior, how its shape distorts, and how its pulsations behave over time. Properly modeling rotation requires significant additional complexity, and many standard evolutionary models therefore omit it or treat it only approximately, accepting some resulting imprecision as the cost of a tractable calculation. For an unusual star like Polaris, already behaving strangely in its pulsation pattern, the absence of detailed rotational physics in the... A related possibility involves mass loss, the gradual shedding of material from a star's outer layers over the course of its life, a process more pronounced in certain evolutionary stages than others. If Polaris's primary star has lost a meaningful amount of mass over its lifetime, whether through an ordinary stellar wind or through some interaction with its close companion, this lost mass would subtly alter how the star's current properties compare to the predictions of a model that assumes a simpler, unchanging mass throughout its life. Some research has attempted to estimate how much mass might have been lost, though the resulting figures remain provisional, offered as a plausible contributing factor rather than a settled conclusion. And more recently, observations using an array of linked telescopes capable of extraordinarily fine surface resolution detected something on the surface of Polaris's primary star that adds yet another layer to the puzzle. Large, dark patches resembling oversized star spots, the stellar equivalent of sunspots, consistent with the presence of a significant magnetic field. A magnetic field of meaningful strength could plausibly influence how the star pulsates, introducing yet another variable that standard pulsation models do not typically account for in detail. Sit for a moment with what all of this adds up to. Polaris's primary star is pulsating in a way that has reversed direction twice over the past century, without a settled explanation. Its distance from Earth, despite being one of the closest examples of its category of star, remains genuinely disputed among careful, well-equipped researchers. Its companion appears to be billions of years older than the primary star itself, a mismatch that violates the simplest expectation for how gravitationally bound stars ought to form together. And the standard models used to predict how stars like this should behave may be missing real physics, rotation, mass loss, magnetic activity that could meaningfully account for some or all of these anomalies, if only that physics could be properly incorporated. None of this is presented as alarming. It is not. Nothing about Polaris's strangeness threatens anything, changes anything about tomorrow, or requires any kind of urgent resolution. It is simply a quiet demonstration of something this channel has returned to on previous evenings, that the things we trust most completely are not always the things we understand most completely. Polaris has been trusted, relied upon, navigated by, for thousands of years, precisely because it appears so simple from where we stand. A single steady point, doing one steady job. And the closer it has been examined, the more that simplicity has revealed itself to be a kind of distance-induced illusion. The same blurring of complexity into apparent calm that distance creates for so many things explored across these evenings. Whether it is the true scale of a spiral arm compressed into a few centimeters on a diagram, or the true population of a triple star system compressed into a single point of light, there is something gentle worth noting in why these particular puzzles matter beyond Polaris itself. The category of pulsating star that Polaris belongs to is not merely a curiosity. It is, as described earlier, one of the foundational tools astronomers use to measure the scale of the observable universe, the rung on the cosmic distance ladder that bridges measurements within our own galaxy to measurements of galaxies millions of light years distant. If something about how this entire category of star pulsates and evolves is not fully understood, if the standard models used to calibrate their brightness are missing some piece of physics that Polaris's strangeness happens to be revealing, the consequences ripple outward far beyond this single star. They touch the calculated distances to other galaxies, the inferred rate at which the universe is expanding, the broader picture of cosmic history that depends, in part, on trusting that this particular category of standard candle behaves exactly as the models predict. This is why a single, nearby, oddly behaving star receives this much careful, patient attention from researchers, year after year, decade after decade. Not because Polaris itself is in any danger, or because its mysteries pose any practical problem for anyone navigating by it tonight, but because There is also a slower, gentler thread running beneath all of this, one connecting tonight's exploration to an earlier evening's consideration of how the sky itself changes shape over very long stretches of time. Polaris has not always been the North Star, and it will not remain the North Star forever. Earth's rotational axis does not point in a perfectly fixed direction across the centuries. Instead, like a slowly spinning top whose axis traces a wide, lazy circle, Earth's axis gradually sweeps through a long, slow cycle, pointing toward different stars at different points across many thousands of years. Several thousand years ago, the axis pointed toward an entirely different bright star, one now associated with summer skies rather than steady northern navigation. Many thousands of years from now, the axis will return to point toward that same star once again, having completed its long, slow circle. Polaris, then, is not some permanent cosmic fixture chosen by the universe to mark north for all time. It is simply the star that happens, for this particular multi-thousand-year window of Earth's slow wobble, to sit closest to the direction Earth's axis currently points. Future generations, far enough removed from now, will look toward a different point in the sky entirely when they search for steady north. And Polaris will, for them, simply be one more star among many, drifting slowly across the sky like everything else, no longer singled out by the particular geometric coincidence that has made it so useful to us. Gather the threads now, gently, the way previous evenings have gathered theirs. The first thread is structural. Polaris is not one star but three, a bright, evolved giant accompanied by two fainter companions, one close and one distant, bound together by gravity into a single system that has only gradually revealed its true composition across more than 2 centuries of increasingly careful observation. The second thread is rhythmic. Polaris belongs to a category of pulsating star whose brightness cycle reveals its true luminosity, making it one of the foundational tools for measuring distances across the universe. Yet its own pulsation has behaved unpredictably, its amplitude declining for decades before mysteriously recovering, its period lengthening for generations before mysteriously reversing, with no settled explanation for either change. The third thread is geometric. Despite being remarkably close by astronomical standards, Polaris's distance remains genuinely disputed, complicated by its brightness, its pulsation, and the presence of its nearby companion, each factor compounding the difficulty of an otherwise straightforward measurement technique. The fourth thread is temporal. The measured ages of Polaris's primary star and its close companion do not comfortably match, a mismatch that challenges the simplest expectation that gravitationally bound stars should share a common birth, and that may point toward a stellar merger or some other unusual event in the system's deep past. The fifth thread is theoretical. The standard models astronomers use to predict stellar evolution and pulsation behavior may be missing real physics relevant to a star like Polaris, the effects of rotation, of gradual mass loss, of magnetic activity revealed by recent high-resolution surface observations. Incorporating this missing physics more fully may eventually resolve some of tonight's puzzles, though that resolution remains for now a work in progress. The sixth thread is consequential, reaching beyond Polaris itself. Because this category of pulsating star underpins so much of how astronomers measure distance across the universe, understanding precisely why this one nearby example behaves unusually carries weight far beyond a single star's curious history, touching the broader, careful work of mapping cosmic distance seventh thread, and the gentlest, is about permanence, or rather, its absence. Polaris's role as the North Star is a temporary geometric coincidence, the product of Earth's slow axial wobble, currently pointing in this particular star's direction. In time, that wobble will carry the celestial pole elsewhere, and Polaris will quietly return to being simply one star among the many scattered across the northern sky. Its long service as a fixed point in human navigation, no more permanent than any other arrangement the slowly turning sky has offered, and will continue to offer long after tonight. There is a quiet symmetry in arriving here, the same kind of symmetry that has closed previous evenings. The star we have trusted most completely, precisely because it appears so simple and so steady from where we stand, turns out, on patient examination, to be a small system of 3 stars whose pulsation defies easy explanation, whose distance resists precise measurement, and whose 2 principal members appear to disagree, by the ordinary rules of stellar evolution, about how old they actually are. None of this diminishes Polaris's